Welcome to today's 7th lecture. We'll discuss single supply class AB push-pull amplifier. In this lecture, we have already studied the theory for this amplifier and class AB amplifier. And in this lecture, we will solve a numerical problem for this. We have this VCC and this ground, so it's different from the class AB power amplifier, push-pull amplifier, where we have this plus VCC and minus VCC. So it's a different circuit, and for that we know that it is biased at VCC by 2 instead of being biased at is equal to 0 volts as it was in case of a dual power supply system. It's not biased at 0 volts at the output. The output DC voltage is VCC by 2. Therefore, we have this input coupling capacitors and output coupling capacitor because the voltage here is VCC by 2 plus 0.7. So in order to stop that voltage, to flow, to cause any current flow through this AC source, we have these coupling capacitors R1 and R2, and the output, we want the AC output signal swinging at 0 volts. Therefore we have this coupling capacitor, the output coupling capacitor. The remaining side is the same D1 D2. We have attached D1 D2 to avoid crossover distortion. You already know, and we discussed in our class today. So this is an example where we have this numerical values: plus 15 volt is VCC, R1 and R2 are given to be 1 kilo ohms, and RL, it's not R1, it's RL. Load resistor, it's 75 ohms. And we have to find VB for Q1. You know this VB will be 0.7 volts higher than the voltage at emitter, or the voltage that we have at emitter because it's an NPN transistor. So the voltage of emitter is biased at VCC by 2. So the voltage of emitter for both this NPN and this PNP transistor, it's equal to VCC by 2. So it's 7.5. 15 divided by 2, it's 7.5. So 7.5 plus 0.7. So VB at Q1 is 8.2 volts. VB at Q2 will be smaller than the voltage at its emitter. How much? By 0.7, since the emitter is 0.7 volts higher than the base, so VB would be VE minus 0.7. So emitter is at a higher voltage, VB is at a lower voltage, a smaller voltage. So VB at Q1 is higher than the output voltage. VB at Q2 is 0.7 smaller than the output voltage. So we are talking about DC voltages. VE is the same as VCC by 2, 7.5 volts, the same DC voltage that we have at the output. So in part A, we're going to find ICQ. ICQ is the same that we studied in last lecture. It's VCC minus VB1 divided by R1. So IC would be, since the current mirror, the current that flows here is the same as the current that flows here. So VCC minus VB divided by R1 is the same current flows here, the same current flows here. So IC is the same as VCC minus VB1 over R1. Plugging these values in 15 minus 8.2 divided by 1, it comes out to be 6.8 milliamp. And this current is the same as the current that flows through the collector of transistor 2, Q2. And then we have to find VCE of Q1. VCE for Q1 is, the voltage of emitter is 7.5. The voltage of collector. Its collector is at 15 volts, and this collector is at 0 volts. So VCE for Q1 would be 15 minus 7.5. And what would be VCE for Q2? 0 minus 7.5, so negative 7.5. So this answer is 7.5. This is negative 7.5. So 7.5 and negative 7.5. VCE for Q1, VCE for Q2. And then in the second part, it's not the last part. Second part, we are given that Vin is 10 volt peak to peak. Now we are given another information about the circuit as this Vin is given to be 10 volts peak to peak. So what would be the peak voltage? Of course, that will be higher than that will be 1/2 compared to this peak to peak voltage. That will be 5 volt peak. And what will be the RMS? 5 times 0.7 or 7 will be the RMS voltage. So computing RMS voltage first. So Vin 10 volts peak to peak means 5 volts peak, and multiplying with this 0.7 or 7, it comes out to be 3.54 volts RMS. So what should be the power dissipated? The same voltage appears at the output divided by RL. The same voltage that appears at output divided by RL. There is no voltage drop here because it's already biased at 0.7 volts. So it's already, the junction is already forward biased. This base emitter junction is already forward biased. We get the same 3.54 volts RMS here. So we have this VL 3.54 square it divided by RL will give you the power dissipation. So 3.54 square divided by 75 is 167 milliamperes. And the third and the last part is to find PL max. To find PL max, we have to find VL max first and then IL. PL max can be VCC by 2 and RMS value would be multiplied by 0.707. IL max is VC VL max divided by RL. That comes out to be 70.7 milliamperes. So now we have computed VL max, IL max, multiplying them will give us PL max. So multiply these two gives us 375 milliwatt, the maximum PL that we can have across this RF, 375 milliwatt. And what is the actual power dissipation that we are getting right now? It's 167 milliwatt, quite small. 167 versus 375. So we are working at around 40% of the maximum power that we can have at RL, at the output dissipated in RL. So we have a homework today. That homework is that if the VCC is raised to plus 24 volts instead of, what is it right now? What is it right now? It is 15 volts right now. So if we raise it to 24 volts from 15, what is PL max? This is your homework. You have to repeat some parts, maybe something from part 2 and part B and part C. VCC is raised to 24 volts, so you have to compute some quantities, and you will finally see that PL max would be different from this PL max. So you have to compare these two PL max. This PL max is for VCC is equal to 15 volts. So you have to compute new PL max. You have to solve part C once again. You have to compute new PL max for this VCC, 24 volts instead of 15 volts. So this is your homework. Right, that's all for this lecture, and from the next lecture onwards we will be studying class C amplifiers. Thank you.